The impossible galaxies. Start with a room that smells like coffee gone cold. A small team sifts through deep fields, CERS, JADES glass, searching for the faintest red smudges. Photometry puts them at redshifts 10, 12, 15. Translation: we're looking less than 400 million years after the Big Bang. Then the FITs return stellar masses flirting with 1 billion suns or more and star formation rates like factories on double shift. The channel goes quiet. Someone types, "Too big, too soon." Hear why that phrase stings. In the standard lambdictum playbook, tiny fluctuations seeded by inflation grow under gravity. Dark matter halos collapse first, gas cools, stars ignite, feedback throttles the frenzy. It's not leisurely, but it's not instant. By Z10, you expect scrappy, blue, low-mass clumps, not mature systems with dense stellar bulks and rest-frame optical light strong enough to fake middle age. So the first question is basic. Are they really that far? Photometric redshifts can lie. Strong emission lines can boost flux in filters, dust can redden a closer galaxy into a distant imposter, and active nuclei can masquerade as mass. Teams sprint for spectroscopy. Lyman breaks, nebular lines, clean features that pin distance. Some candidates slide down to Z57 after spectra. Others hold the line. A few even push higher. The universe breakers don't disappear. They thin, then regroup. Next comes mass. Photometry infers stellar mass by fitting spectral energy distribution. Essentially, what mix of stars best explains the colors. But if nebular emission fills the bands, you overcount starlight. If the initial mass function is top-heavy, you overweight big stars. If a hidden AGN contributes, you inflate the total. With better modeling, allowing strong lines, bursty histories, and AGN components, some masses tick down. Yet a stubborn subset stays hefty. As of 2024-2025 analyses, catalogs still show roughly twice as many massive systems at these epochs as baseline lambdictum simulations predicted. The panic softens into tension. The schedule is tight, not shattered. Now surface brightness. Redshift dims a galaxy's brightness by 1 plus Z4. High Z disks should look tiny and faint per unit area. Early JWST images showed larger than expected apparent sizes for some candidates. Lensing can magnify and stretch, hiding foreground tricks. Survey teams remeasure with careful lens maps, some shrink. But even after debiasing, bright overperformers dominate the catalogs. That's selection. We see the luminous tail first. It doesn't erase the tail. Why too big, too soon matters isn't just star counts. It's chemistry. Metallicity rises as generations of stars live and die. Seeing relatively enriched gas early implies fast cycling, stars forming, exploding, seeding, and reforming on compressed timescales. It's also surface brightness and compactness, tight stellar cores hinting at rapid assembly, possibly through gas-rich mergers or violent disk instabilities. What fixes help? Efficient physics at dawn. Metal-poor gas cools via molecular hydrogen and fine structure lines. Under the right conditions, it fragments hard, feeding extreme starbursts. Early black hole seeds, remnants of massive population III stars or direct collapse candidates, can accrete, their feedback compressing or clearing gas in cycles that actually hasten growth. Subgrid models in simulations, those compressed rules for unresolved physics, get retuned. Stronger early cooling, burstier star formation, anisotropic feedback. The result? Galaxies that build faster without breaking late-time statistics. Meanwhile, observers hedge their bets with alternative levers. If the present expansion rate h is higher than CMB inferred values, the look-back time to a given redshift shrinks. A faster clock makes impossible growth less impossible. That's the Hubble Tension's shadow creeping into dawn. But even with a modestly shorter timeline, you still need efficient channels. Lensing and selection effects sit on the witness stand. Strong lensing can boost counts and brightness, biasing catalogs to rare, magnified systems. Survey teams cross-match with mass maps to flag the culprits. Some early headliners fall into this bucket, others don't. The net? Corrections help. They don't acquit the schedule. Here's a micro story that humanizes the curve. A grad student stacks cutouts of a candidate at Z-13, heart thumping as the pipeline returns a clean Lyman break and no obvious low Z solution. Weeks later, the spectrograph delivers a line faint, but right where it should be. Her mass estimate drops after she includes nebular contamination. The galaxy is smaller than the first fit. It's still bright. It's still early. She doesn't pop champagne. She updates the plot and adds a footnote. Efficient physics required. There's an irony tucked in here. The same lambdictum that nails the acoustic peaks in the cosmic microwave background and the clustering of galaxies at low redshift can, with modest retunes, absorb faster early assembly. Tilt the scalar spectral index within bounds, adjust sigma 8 slightly, allow for higher early star formation efficiency in dense halos, and your simulations spit out more luminous juveniles. The scaffolding doesn't collapse, it flexes. So what still stings after the dust settles? The ledger of early light. Even with corrected masses, careful sizes, and conservative fits, the bright tail is crowded. The number density of massive, compact systems appears elevated. Chemical clues hint at quick enrichment. Surfaces shine harder than naive models expected. That doesn't mean the Big Bang is false. It means the first chapter read faster, the pen wrote with a finer nib, and our subgrid notes were too simple. Which sets up the next move cleanly. If the late-time anchors of lambdictum are firm, maybe the crack sits closer to the opening pages, the initial conditions, the inflationary seeds, or the way we translate photons into histories. And if the cosmic clock itself is off by a few beats, those galaxies stop being miracles and start being milestones. The 13.8 problem, how we nailed the age. To see where the schedule came from, you have to stand in a control room built out of fossils of light. The number on the whiteboard, 13, 8 billion years, wasn't guessed. It was triangulated, pinned down by 3 independent yardsticks that don't share the same weaknesses, then cross-checked until the error bars stopped shrinking. Start with the oldest messenger, the cosmic microwave background. Freeze the universe about 380,000 years after the Big Bang, when electrons finally married protons and light could travel. That light, stretched into microwaves by expansion, arrives today as a near-perfect blackbody with tiny temperature ripples. Plot those ripples into a power spectrum, and a comb of acoustic peaks appears. Those peaks are sound waves in the photon, baryon plasma, imprinted at recombination. Their positions and heights encode the matter content, baryon fraction, curvature, and expansion history. Feed that to lambdictum and you get a tightly constrained set of parameters. One of them, when evolved forward under the model's rules, gives you the current expansion rate, and by integration, an age. Planck's data favored an age right around 13.8 billion years, and a present H near 67 km/s/MPC. That's one leg of the stool. Next, fold in baryon acoustic oscillations, those same primordial sound waves, now fossilized as a preferred clustering scale in the distribution of galaxies. Map millions of galaxies in 3 dimensions, and you find a subtle excess of pairs separated by about 150 megaparsecs. That scale is a standard ruler. Measure it at different redshifts, and you get the expansion history in discrete slices. Bow doesn't care about supernova calibrations or stellar physics in distant hosts. It tracks geometry. When combined with CMB constraints, it nails down the distance, redshift relation with impressive precision. The ruler agrees with the microwave sky about the overall story and, crucially, the age. Finally, bring in standard candles. Type Ia supernovae, white dwarfs ripped over a mass threshold, explode with remarkably similar peak luminosities. Calibrated properly, their brightness becomes a distance indicator. Plot distance versus redshift, and you get the signature of acceleration that led to dark energy, the lambda in lambdictum. The supernova Hubble diagram alone can't give you an absolute age without assumptions, but when you anchor it with local distance ladder calibrators, Cepheid variables, the tip of the red giant branch, and compare with BOW and CMB, you lock the story together. Multiple ladders, different rungs, converging on a consistent timeline. If you're keeping score, this is why cosmologists don't panic easily. The CMB acoustic peaks, BOW measurements, and supernova distances are independent lines of evidence that fit a compact model with few parameters and wide reach. Adjust one lever, and the others respond in predictable ways. You can quantify the age because the framework tying these data together is not a jigsaw puzzle with pieces forced to meet. It's a differential equation with well-measured inputs. But here's the caveat the late-night slack threads circle. Agreement depends on early universe assumptions. Inflation smoothed the initial conditions and set a nearly scale invariant spectrum of primordial fluctuations. The sound horizon at recombination, the physical size of those acoustic ripples, depends on the energy content and expansion rate before and during that era. Change the early recipe, and the ruler you've been using shrinks or swells. Early dark energy can punch the expansion briefly, reducing the sound horizon. Neutrino physics can tweak the radiation density. Even subtle features in the inflationary potential can imprint small deviations that propagate into present-day inferences. That's where the 13.8 becomes less like a birth certificate and more like a contract. Within lambdictum rules, the number is solid. Step outside the rules, and you're renegotiating the terms. The Hubble tension lives exactly in that space. Local measurements, distance ladders and time delay lenses, prefer a faster expansion today than the CMB-anchored model implies. One way to reconcile them keeps the late universe intact, but alters the early chapter, shaving the ruler to let both sets of data fit. A shorter sound horizon means you can hold the microwave background in place and still allow a higher H. The integrated age can shift slightly without demolishing everything else. Meanwhile, caution signs blink. Some JWST-assisted calibrations of local distance indicators nudge values in different directions. Reanalyses of Cepheid hosts, the use of red giant branch tips and lensing-based H all try to avoid shared systematics. The trend holds. Late time probes point higher, early time probes point lower. The stubbornness of the mismatch is the point. If you can't make it go away with reasonable systematics, you're forced to ask if the early assumptions need revision. None of this rescues every oversized galaxy on its own. Even with a slightly younger clock at a given redshift, those bright outliers still demand efficient formation. But it reframes the rigidity of the schedule we thought we had. The age came from a chorus. The harmony remains, but one section is singing a different tempo. So when someone says the universe is 13.8 billion years old, the honest addendum is under the lambdictum score. The strength of that statement is how many instruments are in tune. The opportunity, the crisis, if you like, is that the few out-of-step notes might be telling us the opening bars weren't quite the ones we printed. Inflation's promise and its blind spots. To see how the first pages could run faster without wrecking the ending, you have to sit with the wildest quiet idea in cosmology: inflation. Not an explosion, but a blink of accelerated expansion that takes a tiny, causally connected patch and stretches it until regions that once shared a thermometer now sit billions of light years apart. That single move solves 3 headaches at once and sets the stage for everything we measure later. Start with the horizon problem. The cosmic microwave background looks uniform to 1 part in 100,000 across patches of sky that, under slow expansion, could never have exchanged so much as a photon. Inflation says they did before the stretch. Those regions were neighbors. They equilibrated, then got pulled apart faster than light can knit them back together. Uniformity isn't a miracle, it's memory. Next, flatness. General relativity allows space to curve like a saddle or a sphere, but precision maps show our universe is very close to spatially flat. Inflation irons curvature the way tension flattens a wrinkled sheet. Enough E folds and whatever bend you started with dilutes to nearly zero. You do, Fine-tune initial curvature, you erase it. Then the seed problem. Where did the tiny over and under densities come from? The ones gravity would later amplify into galaxies, clusters, and voids. Quantum fields can't sit perfectly still. They jitter. During inflation, microscopic fluctuations get stretched to astronomical scales. Modes cross the horizon and freeze, leaving a nearly scale-invariant spectrum of perturbations. After inflation ends and the universe reheats, those ripples re-enter the horizon. The photon-baryon plasma rings like a drum, imprinting acoustic peaks in the microwave sky. The statistics, almost Gaussian, slightly tilted, match what telescopes see. That's not hand-waving, it's a predictive fingerprint. There's beauty here. A small set of parameters, the amplitude of fluctuations, their tilt, the baryon fraction, the matter density, describe both the speckled microwave wallpaper and the large-scale structure scaffolding. Inflation, as a class of mechanisms, links the smallest physics we can't see directly to the largest patterns we can. But the pen that writes neatly also smudges. Inflation successes arrive bundled with blind spots. The first is the engine. In the simplest stories, a scalar field, the inflaton, rolls down a flat potential driving accelerated expansion. We don't know what that field is. Many potentials can do the job. Whole families survive current constraints. Flexibility lets inflation accommodate data. It also makes specific predictions slippery. If dozens of models fit, which one, if any, is right? Look for a decisive signature. Primordial gravitational waves. Inflation stretching spacetime itself should launch a background of tensor modes that polarize the microwave background in a curl pattern, B modes, on large angular scales. Experiments have chased that signal for a decade, setting upper limits that squeeze large field models where the inflaton traverses big distances in field space. So far, no confirmed detection. That's informative. Many versions get pushed to the margins, but it's not a kill shot. Then there are the anomalies that cling to the low multipoles. The quadrupole power sits low. Some alignments in the largest modes, the cheekily named axis of evil, won't quite die. Hemispherical power asymmetry lingers at low significance. These could be statistical flukes in a vast sky. The look elsewhere effect is merciless. Or they could whisper that inflation wasn't perfectly simple, that the potential had a feature, a pause, a bend that left a bruise. The data don't force a rewrite. They do keep theorists honest. Another concern, initial conditions. Ironically, a mechanism designed to wipe away sensitivity to the start seems to require a patch where the inflaton field is already smooth enough and high enough on its potential to begin rolling. Some argue that in a messy quantum gravity prelude, such patches are natural. Others aren't convinced. It's an argument about measure in a space of possibilities we don't yet calculate from first principles. Push further and you hit eternal inflation. In many models, while our patch exits inflation and reheats, other regions keep inflating. Quantum fluctuations kick the field uphill as often as down in some domains. The result is a bubbly multiverse where pocket universes like ours nucleate endlessly with different low-energy properties. It's a legitimate mathematical outcome of certain potentials. It also raises a testability problem. If most of the structure lies forever beyond our horizon, how do you confirm or falsify the picture? People have hunted for bubble collision scars in the microwave background. Nothing definitive. Maybe they aren't there. Maybe the signal's too faint. Maybe our patch is lonely. There's also a practical blind spot tied to the very success you admired 2 minutes ago. Because inflation can generate the right spectrum of perturbations across a wide range of potentials, you can tune details to fix mismatches at the edges, small features to explain a dip, gentle running to ease a tension, without clear guidance from fundamental physics. It's a flexible pen. That's a virtue until it becomes a vice. So where does that leave the too fast at dawn problem? If the seed's inflation set were slightly different, if the tilt favored a bit more large-scale power within current bounds, if non-Gaussianity on small scales were just enough to enhance early collapse without violating constraints, You'd help dense halos form sooner. If reheating left pockets with unusual thermal histories, you tweak cooling. These are not free passes. They're levers within a framework that already matches most of what we see. The honest read is this: inflation earned its place by solving old problems and predicting new structure that we later measured. Its blind spots aren't fatal, they're invitations. The decisive tests, B-modes, small non-Gaussianities, features, are coming with sharper instruments. Until then, treating inflation as the default doesn't mean pretending it's done. It means letting its economy do work while we probe its edges. And if the opening chapter ran faster, the pen we already hold might still be the one that wrote it, just with finer strokes than our first sketches allowed.